6.2, keeping heat at home. So heat leaks through windows, doors, and walls and roofs of homes. So we want to slow that down because we don't want to be continuously pumping warm air into our house if it's just leaking. Therefore, we use insulation to slow the heat transfer. Insulation keeps warm air in during the winter, but it also keeps warm air out during the summer. It's a barrier for the transfer of heat. Empty space inside and outside walls of house, a wall cavity, need to be filled with insulation to prevent convection currents from heating or cooling the house. Let's take a look at all of these ideas. So, if our house is not insulated, heat can pass quite easily in and out of our house. So, to prevent this, we insulate our house in the roof space, the walls, and then also we take a look at our windows and our doors and we make sure that those have some sort of insulation as well. So that when we have warm air in the house, it has a harder time escaping outside the house. Again, this also helps because on a warm day outside in the summer, there's lots of warm air outside. If we kept all of the windows and doors closed, which seems counterintuitive, it's harder for that air to get into our house, our warm air to get into our house because it has to pass through the insulation, and that heat transfer is slowed by any sort of insulation. Now, what happens if we have a cavity inside our house? So if this was like the siding on the outside of our house, I'm a really great artist, stay tuned. And then these were the walls on the inside of our house. So the drywall on the inside, and this is our siding on the outside. We put insulation in here. Usually it's a fiberglass insulation. We can also use spray insulation. There's a bunch of different types. However, if we didn't do that, and we had lots of nice warm air over here and cool air over here, we use convection where this air inside starts circulating. It heats up using the inside wall. It rises and cools against the outside wall. And we start to get this transfer of energy. And some of our warm air is going to start escaping out. So again, we use insulation here. And it prevents this transfer from happening or very much slows it down. So an R value is a measure of how well an insulating material slows heat transfer. The higher the R value, so a large number, means a better insulator, and it would be a slow heat transfer, which is what we want in our houses. If it is a small value, it's a poor insulator, and we're going to have a very fast heat transfer, which is not what we want. So, which insulation loses heat faster, R12 or R16? Well, we would say that R12 would be found here. R16 is a higher number. So R16 is a better insulator and R12 is a poor insulator. So which one loses heat faster? Well, we have a fast heat transfer the smaller the value. So R12 because it's a smaller R value. So combinations of materials, the R value becomes the sum of each material used. So if I use insulation and I use maybe concrete, which is an insulator still, I will add both of their R values together to get the R value used. So here's an example. We have a table of R values over here, okay? And these are based on specific thicknesses of these materials. My goodness. Okay, so the walls of your home have 25 millimeters of expanded polystyrene. Okay, so we have 25 millimeters of expanded polystyrene and 25 millimeters of rigid urethane foam. So this one. What is the total R value of your insulation? So we're going to take the R value of each, so 3.96, and we're going to add it to the 7.50, and we'll get our total. The total combined R value will be 11.46. Now, what happens if we add a thicker layer? So let's look at the same question, but let's have different thicknesses. Let's have 75 millimeters of expanded polystyrene and 50 millimeters of rigid urethane foam. Okay, so 25 millimeters, we actually had 75 here. To get from 25 to 75, I multiplied by 3. Therefore, I need to multiply this R value by 3 to get the total R value of 75 millimeters of expanded polystyrene. So 3.96 times 3 is 11.88. And this, again, was from our 75 millimeters of expanded polystyrene. All right, our next one, we had 50 millimeters of rigid urethane foam. To get from 25 to 50, I had to multiply by 2. So I'm going to do that same thing to our R value. So 7.5 times 2 is 15. Now, because these are added together, rigid urethane foam. Because those are combined to create the insulation, we need to add those two values together. Using my calculator, I got 26.88 as our combined R value. So I can increase the R value two ways. I can combine materials, or I can increase the thickness of insulation. Two ways to increase the R value. All right, windows are constructed of panes of glass from 1 to 3. In 2006, so not that long ago, double pane glass windows became the standard in all new homes. Prior to that, it was a single pane window. So a single pane window just means there's one layer of glass between the inside and the outside of the house. A double pane window has 2 layers of glass between the inside and the outside of the house. They are not touching. They have an air pocket in between. Now, just as it sounds, a triple pane has 3 panes of glass between the inside and the outside of the house. In between these panes of glass, they are not pressed right up against one another. You will see that there would be an air pocket. You could actually go look at the windows in your house, take a look at the bottom track, and you should be able to see how many panes of glass there are based on kind of the spacing in between. Okay, go take a look at your windows and figure out what you have in your house. All right, so why is a single pane not as energy efficient as a double pane window? Well, a single pane window, energy can be transferred directly through the glass. Okay, so we have to use just conduction. The warm air inside our house heats the glass up, which can then pass to the air outside. A double pane window, we have to use conduction to heat the inner pane. And then we have to use convection within this space to heat the outer pane. And once the outer pane is heated, we can use conduction again. Remember, every time energy is transferred, we lose some of it. So we're losing energy every time we do this, and we're not going to lose as much from our house. All right, the transfer is much smaller in this double pane because it has to go through 3 different processes to get outside. This would be expanded even further in a triple pane window. We'd have to use conduction to heat this, convection within, conduction and convection, and then conduction again. So the more layers of glass, the better. At this point, there's no such thing as a quadruple pane window. Triple is the highest you can go. So what would you expect the R value of a triple pane glass window to be? So you can see here that the R value of one thickness of glass is 1. The R value for 2 thicknesses with an airspace in between is 1.8. So I would expect that if this is increased, we would get an increased R value. So it would be greater than 1.8. Again, our single pane of glass is a poor insulator. Heat escapes quickly through glass. Leaks are common around panes and edges of windows. So leaks around where one pane of glass ends is quite common, and leaks around the edges of the windows and the openings are common. Older windows had double windows and doors, but they actually just put 2 layers of windows or doors. So we would have like an interior window and then an exterior window. And whether they had a patio out here or not, sometimes that was common. If you look at older homes, sometimes a full external patio is glassed in. So not only could you sit out there because it's a little bit warmer in cooler months, but it prevents the heat transfer from outside, inside, and vice versa. Same thing with doors. Some people have 2 doors on their home where you have to enter both to get in the house. These are called storm windows or doors. They help to keep the heat in because they were just a more primitive way of introducing this air pocket in between 2. Double pane windows have an air pocket between the 2 panes, which we talked about. The insulation value of this pocket of air is increased when it's mixed with some gases like argon. So in between our 2 panes of glass, we can just use air. But if we put argon in there, the R value increases from just having air. Doors used to be wooden, and heat could just transfer through the wood. It was a little bit slower because wood is a natural fiber or material, and it's made out of cells, and so there were some air pockets in it to help with insulation. However, now we typically have a metal door with a space full of insulation in the middle. Okay. All right, we use insulated things quite regularly. If you have a water bottle or a travel mug, we are trying to keep either the water colder within it, like the Swell water bottles is what I'm thinking about, the metal ones. We try to keep it cooler, and in our travel mug, we're trying to keep our liquids warmer. So how they achieve this is we have 2 containers fitted within one another. So we have an outside container here, and then we have an inside container and our liquid inside that interior container. So these 2 containers are fitted together, and the air in between is kind of removed. So we make a vacuum. All right, so there's not as much air in this purple space as there would be just outside, like regular in our atmosphere. So hence the name vacuum. Sometimes we can also add some extra insulation in here to keep these from cooling or transferring their energy. The inner layer, so inside our bottle here, is reflective. And this helps to reflect heat back in. So when heat is trying to escape from our water, let's say this was keeping it warm, it kind of bounces back and is reflected back into the container with a reflective surface. If it isn't a reflective surface, it can transfer through. This helps with our radiation. Okay, like our infrared waves that are trying to escape through. So, how does the bottle prevent conduction? Remember, conduction is when two things are touching. Well, we have an inner and an outer layer that are not touching. Inner and outer layer don't touch. How do we prevent convection, which is those currents? We prevent it by giving a vacuum, so there's no air there, or insulating. A vacuum between layers, so there's no air to circulate. And some insulation. Let's say and or some insulation. And radiation is prevented. Again, these infrared waves cannot get out because it is reflective. Inner layer. So infrared rays / waves, I guess I should call them, are reflected back. Large appliances we know are insulated in our kitchen, like the fridge, the stove, the dishwasher. Sometimes they're kind of hidden within panels, but we are trying to insulate, either keep it warm, like our stove. We don't want all of the energy used to heat it up to come out. We want to be able to keep our baking at 350 so we get perfect muffins. We want our fridge to stay cool, so we insulate it so thermal energy cannot enter it as easily. And our dishwasher, typically we wash our dishes on a hot cycle, and we want to keep that energy in, not only because it's energy efficient, but we also just don't want to wreck our cabinets. If there's lots of heat coming out of these things, our walls and our cabinets would become damaged. Non-metals are good insulators. Remember this from our chemistry unit. Metals are great conductors of heat. So we use wooden and plastic handles on hot items so that you can pick them up. Like our pots, again, are made out of metal because they're great conductors. They're going to transfer the energy from the burner to the water or soup or whatever you're cooking. But we don't want that heat to be transferred to our hands, so we're going to use something that isn't going to conduct heat. So if you tried to stir something with a wooden spoon versus a metal spoon, the metal spoon is going to get warm, whereas the wooden spoon will not. There's some practice on page 119 of your Science Connect 1 textbook. I'd highly recommend taking a look at it.